Whoa! I never thought about that!
Okay, think about this for a second. Our home, the Earth, is literally an enormous spinning rock hurtling through the vacuum of space, right? And a massive, massive portion of it is completely covered in water. Yet somehow, we don't just lose all our oceans into the void. Today, we're unpacking the mechanics behind this absolutely incredible balancing act and exploring exactly how our oceans stay so firmly put. Let's get right into it. It's a question of monumental planetary physics, honestly. Why doesn't the water just spill over onto the land? I mean, why aren't our continents constantly flooded? And why doesn't the water at the quote-unquote bottom of the globe simply drip off into space? You know, we completely take it for granted that the beach just naturally stops where the sand starts, but the actual mechanics keeping those oceans in their designated zones, they are nothing short of spectacular. So, this perfectly tuned system really comes down to three main factors: gravity, the shape of the Earth, and motion. Section 1. Gravity, the ultimate anchor, redefining the way things fall. Okay, to really understand how gravity manages our oceans, we require a complete perspective shift. Now, when you drop an apple, you'd say it falls down, right? But on a planetary scale, down simply means toward the center of the Earth. It's not a universal direction in space. Gravity pulls absolutely everything toward that extremely dense core. And yes, that includes every single drop of ocean water. So instead of water falling off the bottom of the globe, it is fiercely sticking to the Earth in all directions. The oceans aren't just politely sitting on top of a flat surface, they are actually wrapped around a sphere, pulled inward by this relentless anchor. That's exactly why a ship sailing near Antarctica isn't just falling into space. Gravity's inward pull secures roughly 332 million cubic miles of water. That is so much water, and it's held there like an incredibly tight liquid skin. Section 2. Earth's natural ocean basins. Why the water stays off the land. Which brings us to sea level balance. Imagine you're pouring water into a bowl that has a large rock sitting inside it. The water naturally settles to the lowest possible level, right? It surrounds the rock, but it doesn't cover it. Well, Earth's land acts just like that rock. Our continents actually sit on a thicker, lighter crust, leaving them much higher in elevation. Meanwhile, the ocean floors are lower and denser. So under gravity's massive pull, the water rushes to fill those really deep regions first, leaving the higher crust totally exposed. Section 3. Why spin doesn't spill. The battle of planetary forces. Get this, Earth is spinning at roughly 1,000 miles per hour at the equator. With that kind of speed, you'd probably think the outward centrifugal force would just fling the oceans straight into space. But imagine swinging a bucket of water in a circle. The water stays in the bucket because of the outward force. Now, Earth is actually the opposite scenario. Earth's gravity is the absolute heavyweight champion here, vastly overpowering the outward push of the spin. So the water does try to push away, but gravity easily, and I mean easily, pulls it right back down into those deep basins. Section 4. The true shape of Earth. How our planet's form dictates the oceans. Now, because of that intense 1,000 mile per hour spin, the Earth actually isn't a perfect sphere. It bulges out at the equator, making it about 26 miles wider there than it is from pole to pole. Scientists call this stable, slightly flattened shape the geoid. And because water is a fluid, it just naturally molds perfectly over this irregular shape. The oceans are quite literally contouring themselves to the Earth's specific, unique gravitational footprint. How cool is that? So how do we actually know all of this invisible physics? Well, it all started with Isaac Newton, first explaining the mathematics of gravity. But today, we've taken his foundation straight into orbit. We use highly advanced satellites like the GRACE mission to measure microscopic changes in Earth's gravitational pull. That's how we map that exact geoid shape and track exactly how the oceans distribute themselves. It is just a beautiful marriage of classical physics and modern space technology. Okay, to truly test our understanding of this delicate balance, let's ask a pretty provocative question. What if the Earth suddenly just stopped spinning? Think about it. If that spin stopped, the outward centrifugal force would completely disappear. And because of gravity and the flattened shape of the planet we just talked about, all that water currently bulging at the equator would start to migrate toward the poles. It would completely reshape the globe. We're talking about drowning northern landmasses and exposing an entirely new equatorial megacontinent. It's wild. Our oceans don't overflow precisely because gravity, rocky elevations, and planetary spin are existing in this perfect harmony. But it really leaves you wondering, if just a slight change in Earth's spin could completely redraw our map, what would happen to our oceans if the moon suddenly vanished?
And that's just one tiny big question. Imagine what's next, subscribe, and let's keep wondering.